Let us define first what is intrinsic material or intrinsic semiconductor material. The best way to describe its definition is that intrinsic semiconductor materials are in its pure form, meaning it is not formed by the addition of pentavalent or trivalent impurities just to make it in a pure form. By this, so holes and electrons are equal. The best example for this material is silicon and germanium that is commonly used in our circuit as the best example for the pure semiconductor. Thank you. For the negative temperature coefficient in terms of resistivity, the resistance increases rapidly with the increase of temperature. However, this negative temperature coefficient is also an effect of a type of solid like semiconductor or insulators, because this doesn't mean that the current will not flow into it. Okay, let us describe the differences between the p-type and n-type semiconductor material in terms of its impurity and carriers. Okay, for the semiconductor materials, it is made by the doping of trivalent impurity to the pure semiconductor. Let's say, for example, the aluminum is doped to a pure semiconductor like silicon. In terms of its carriers, the p-type semiconductor is the majority of its carriers are holes, or what we call the acceptor. Unlike for the n-type semiconductor, it is made from the doping of the pentavalent impurity to the pure semiconductor. So for example, the phosphorus is doped to a semiconductor silicon. The n-type semiconductor has the majority of its carriers are holes, or what we call the donors. So by this, so the p-type semiconductor had low conduction, while the n-type semiconductor has a high conduction. Okay, sketch the conductor, the insulator, and semiconductor in terms of its energy gap or energy band, and explain the differences for these three as well. Okay, for the what we call the insulator, we call the energy. This is what we call the energy. And for this will be the level for this conduction level. In terms of this conduction is the responsible for the electric charge or electric current to pass. This is also for the insulator. Okay, and for this bottom level, this is the what we call the valence band, or the valence band. This is what we call the conduction band. Okay, for this is for the insulator, this will be its band gap. That is for the insulator. This is for the conduction, so meaning the conduction and the valence band, its gap is so high. The gap is so high that is the reason why the insulator will never generate electric charge, because their gap is too high. So let's erase. Next is the what we call the semiconductor material, or semiconductor. Okay, this will be their valence band. Okay, this semiconductor, it's so interesting because it can generate, or it allows the it can conduct electricity, and it can also not conduct electricity. Means it is in a neutral, or it's balanced. So that we can understand, let us illustrate. this will be the a while ago, this will be the gap of the as we see a while ago, and this will be the gap between the insulator and the conduction and the valence band for the insulator. But for the semiconductor, it goes right there. The band gap is just not too high. It's just not too low and not too high. It's just neutral, and this will be its conduction level, or it's in the conduction band. So as you can see, for the semiconductor, its gap is not too high and not too low. That's why it can conduct electricity, and it can sometimes it's the electricity will not pass perfectly, or what we say this very conductive, I mean. So let's proceed for the conductor material. For the conductor material, the example of conductor is metals. So this will be the valence level or the valence band. For the conductor, as you can see, the valence band, this will be the conduction band. So as you can see, it's almost, the levels almost kiss, because as you can see, the band gap is too close, as you can see. So that's why the conductor material is very the passing of the electric charge is smooth and perfect. The differences between this conductor, semiconductor, and the insulator is that this conductor conduct perfectly for the electric charge, while the semiconductor, it could be conduct electricity, or it can be insulate electricity, while the insulator, there is very low chance of, or no chance of the electric charge or energy to pass through it. So that is the differences between the three. Okay, let us illustrate, or let us sketch the p-n junction in terms of its depletion, in terms of the depletion region. Okay, so this will be, let us draw something like this. This will be the p-type and the n-type semiconductor. Okay, let's see examples. Okay, this is just an example. This is really positive, minus. Okay, according to its definition, when the electrons and holes depletes the holes in the p region and the electrons in the n region near the junction. So when it is called depletion, because according for the definition of depletion, it means to reduce or to reduce the quantity of a certain number, either it's p type or it's n type, either the electrons or the holes. So in this case, if the deplete or something is reduced, it can create, or it can formulate some biases, either forward, reverse, or no bias. And okay, let us describe in terms of its current flow. In terms of current flow, let's have some, let's put some direction. This would be negative, it would be positive. So So okay, this would be the depletion region. Okay, no, it's not I, it's E. Okay, this is what we call the holes, and this is what we call the electrons. So therefore, if this will be the holes, the direction of the current flow should be here. This is the holes, because I'll write this correct for the P type. Okay, so okay, right, the holes, the direction of the holes is to the right, because as you can see, the majority of this region is are holes. Okay, while in the end, for the end, this will be the electron. That will be the direction for the majority of this region is the electron. But because of this illustration of this sketch, it will be considered as forward bias. It is called forward bias or forward biasing because it means that putting a voltage across a diode that allows current to flow easily. And in terms of the p-n junction, the n material is called forward bias because the electron moves forward into the holes. As you can see, the n or the electrons move forward into the holes. Okay, but if we reverse the direction, but it will be now called the reverse biasing or reverse bias if you reverse the direction. So as you can see, there is a big differences between the forward and reverse bias because as we illustrate a while ago, the forward bias, it can generate or it can allow electric current or electric charge, while in reverse bias there is no does not allow the current to flow through it. So because the direction and for direction in terms of the junction is opposite to the forward bias. Okay, for what if there is no voltage is applied, what it is called? If no voltage, certain voltage is applied. If no certain voltage is applied, it will be called the neutral or no bias. That's simple, that's basic. If there's no voltage or it's zero voltage applied to a circuit, that will be called a neutral or no bias because it will have no direction and you cannot determine the direction of the current or the electric charge where it should be passed or which allows it through in what direction of a junction.